Hi, everyone, and thank you for the opportunity to speak today. My name is Michaela Leung. I'm currently a fifth year PhD candidate at the University of California, Riverside, where it is currently something like 6 o'clock in the morning, which is why I'm coming to you via video. But I'll be talking to you today about my project on examining the potential for methyl halide accumulation and detectability in Hycean type atmospheres, which is a project that I've been working on for about the past year. It is currently in press at AppJ Letters and available on arXiv, which I'll have a link for you at the end. And I'll be talking about some results that are applicable to life as well. So just for a little bit of background, I first began exploring methyl halides as biosignature candidates in some previous work that I did now a few years ago. And I wanted to show this kind of concept graphic, which demonstrates, we have fluxes of gases produced on the surface. They interact chemically and photochemically in the atmosphere, and the abundances of the gas buildup can show up as potentially detectable spectral features. And because we're thinking about atmospheric chemistry and in particular photochemistry, the type of the star can be really impactful in terms of like what that atmospheric outcome is. And so previously, and this paper is published and you can look it up if you're curious, I looked at methyl bromide in Earth-like atmospheres for FGKM stars, and we found some really promising results that suggest that these are good potential candidate biosignatures. And a large portion of that kind of excitement has to do with the fact that we find significant atmospheric accumulation, and we find that detection could potentially be possible, which I'll talk a little bit more about in a moment. But particularly as biosignature candidates, we think these gases are really exciting because they have low false positive potential. There are very limited abiotic sources. I think you could never really say there's no abiotic sources, especially because we, just don't have enough information to firmly rule that out for most things, but we do find that the abiotic sources that are known are very limited. And that the methylation process, which produces these methyl halide gases, is widespread in a number of different environments and microbial groups. And so as a result, we think that it's a process that potentially could arise again on an exoplanet, maybe a little bit a higher likelihood than other processes that we only see occur in like one particular ecological niche. There is on the Earth very broad spatial and temporal variability in the protection of these gases. And so when I show some simulation results in just a minute, I'll be showing a pretty broad range of gases. And that is kind of supported by the fact that these gases are so variable here on the Earth. And we have, a globally extrapolated flux, but we see local environments that are 100 to 1,000 times and more productive than the globally average levels, which does suggest, again, that it's perhaps reasonable to think these gases could arise in an exoplanet and could be produced at higher levels. And these methylated gases are going to be on the blue circle here on the right. And this is just kind of a general comment, which is that these methylated gases is a really large group of compounds, as well as these halomethanes that are produced by with a similar structure, and that kind of between these two groups we've established or we're working to establish a large number of new candidate biosignatures. So that's kind of the broader context for this specific project. And in terms of the relation to life, the life mission, we did a previous study, which was led by Daniel Angerhausen. This was published last year, looking at the Earth-like simulations for these methyl halide gases. And we do find that you can, potentially detect a number of these features at higher significance. This is for, a TRAPPIST-1-like target for 100 days of observation. We looked at some other durations as well, but I think to really have a strong detection, particularly at more than one wavelength, the 100-day threshold is kind of where we're looking, which is obviously a substantial time investment, but it does suggest that these gases are, not completely out of reach for future life work. And so kind of building on that, we looked originally at Earth-like targets in my previous paper. And so we are considering now upwards in size into this kind of like super Earth regime. And in particular, in the title of my talk, right, it says these Hycean type atmospheres. And so we're thinking in particular of these kind of thin hydrogen envelopes sitting over global oceans. And so kind of essentially thought to be somewhere between, like a true rocky terrestrial planet and like a mini Neptune. I think when we think of a planet for biosignature searches, we're typically thinking of rocky planets. But there's been a lot of theorizing about some of these different super Earth sub Neptune targets to think about if there is any way we could look for biosignatures on those targets, especially right now because these Hycean planets are accessible to JWST. So K218b is kind of the type case for these planets. It's where a lot of the simulating work has been done. And in the past few years, there have been a number of attempts to look at the planet, including now with JWST in transmission. And the fact that we can access these planets now makes them really compelling to work on for a variety of reasons, but also for biosignature simulations and to kind of start to crack away at that problem. And one thing you can see here is this is in the Medusa et al. 2024 paper, they do claim a detection of dimethyl sulfide, they claim it's a tentative, I should say, at kind of a low significance, and this is very controversial. There were a number of papers that came out that were then like, there's other explanations for this gas feature right here, like it might just be methane or something else. So it is a controversial claim of DMS. But if JWST is able to find what could arguably be interpreted as a sign of dimethyl sulfide, which would be potentially a biosignature, that kind of justifies looking for other biosignatures, and especially these other methylated gas biosignatures that are kind of produced by the same process. So that's all kind of just introductory. But to better understand the application of these methylated gases as biosignatures, we use two types of modeling. So we use Vulkan for the photochemical modeling, and then for the spectral modeling, we use PSG and LifeSim. So I'll show you some simulations for JWST, as well as the life simulations, which were done by Daniel and Yanina. So our first result is the kind of on the photochemical side. So we're looking at three different methyl halides: methyl chloride, methyl bromide, and methyl iodide. And we're comparing the Sun and GJ436, which is kind of our, again, type case M star. I believe it's because there are not short wavelength observations of K218, which is the host star for our K218b simulations. So we again show a similar trend, which has previously been recorded for other methylated gases and methane, which is that for an M-type host star, you can see, like 2 to 4 orders of magnitude accumulation enhancement in the atmospheres of these planets. And this is coming from the decreased production of OH under indoor photochemical conditions. And the yellow lines on these plots represent the upper production or the upper mixing ratio values that we find for the Earth-like targets. So you could see that for our more productive methyl chloride case, we can exceed the levels on the Earth, whereas for methyl bromide and methyl iodide, we do see a little bit more of a modest enhancement. I should say that we are using the globally averaged surface flux for each of these gases, and methyl chloride is produced on Earth at higher abundance than the other two gases. So it's possible that were an environment that favored methyl bromide more, we would see methyl bromide being the leading gas here rather than methyl chloride. But for an Earth-like ratio between these gases, we see that methyl chloride continues to have the greatest enhancement. This is a result for JWST. So we have the near spec prism on the left and MIRI LRS on the right. And this was conducted using PSG, and PSG has noise modules for JWST. And what we find is that for a K218b like planet, using near spec prism, you can detect methyl chloride in as few as 5 transits. It turns out that because of, again, the lower abundance of methyl bromide and methyl iodide, they end up not really spectrally contributing. And methyl chloride is what dominates the spectral features. And you can see that in the mid-infrared, we're getting some pretty substantive features, but unfortunately, JWST in the mid-infrared, right, is not doing great, especially for these kind of biosignature searches, because, and you can just see this from the error bars, right, the noise is so substantial in the mid-infrared for the NIRI instrument. So kind of based on this work, we were like, okay, so near spec prism could maybe access these in the near infrared, and then building on the previous work that I had shown for the Earth-like life mission simulations, we also conducted life sim simulations, including for the whole a range of the flux conditions we considered. So we have in subplot A just the regular emission spectrum produced by PSG, and then in B we're looking at the predicted planet yield, and in the kind of like 3 to 5 parsecs, which is where the life simulations were done for, we're kind of expecting to see between like 14 to 30 planets, depending on like how strict the radius requirements are for these Hycean planets, and that's I think not entirely clear at this point, as these are, kind of recently theorized targets. So it seems like the life expected yield for these planets is comparable to what they're expecting for, HWO. So in subplot C, you're seeing our life sim results, which on the top is showing the spectrum, and on the bottom is showing the detection significance. And this is for just 24 hours. And so that you can see these features are even easier to detect than in the Earth-like case for 100 days. So because of the larger size, of the planet and the large size of these features, we really have found that it would be very quick to detect these methylated gases on a K2E like target, which obviously is super exciting because 24 hours is very little observation time, which you can contrast with, again, the 100 days that we were seeing for similar significance levels with the Earth-like targets. So this is a really exciting result. Obviously, on the JWST side, right, this is something that we could potentially look for now and then look for corroborating evidence with something like life, or, if the JWST searches are, unsuccessful or what have you, we could continue to look in the mid-infrared. Oops, sorry, because the mid-infrared features are a little bit larger. They're just primarily being hampered for JWST by the instrument itself. So life would be a great option to look for those larger features and to see if we could potentially detect even like, the lower levels, like the Earth-like or moderately enhanced fluxes, which are not really an option for JWST. For JWST, we're really only looking at the 100 times flux enhancement, which obviously is a substantial global flux. So the life mission might potentially be more sensitive to these gases in the mid-infrared and be able to detect smaller fluxes because the mid-infrared is perhaps more favorable for methylated gases, which is also what we showed in my 2022 paper looking at these methylated gases as well. So kind of in conclusion, we have this JWST result in like 5 transits, and life, we could potentially see a similar detection in 24 hours and or less, 24 hours to get some of those really high significance levels for the higher fluxes. And that for life, we would have, potentially a number of candidates, again, depending on the exact radius limits, but certainly upwards of 10 potential candidates for these Hycean worlds in the expected yield for life, which is really exciting and I think makes these targets really plausible candidates for something you could go after with life. Obviously this is a video, but if you have questions or comments, you can feel free to reach out to me via email. I'm going to move the Zoom thing and hopefully you can scan this archive link. We have the proofs for the paper, so hopefully it will be published in AbJ Letters shortly. And I would also like to thank my co-authors, Shami Sai, Eddie Schwederman, Daniel Angerhausen, and Nina Hansen. And thank you all for listening. And like I said, let me know if you have any questions. Thank you.